This is the third lecture of our training course on design of seismic resistant RCC building. In the previous lecture, we did some ETABS modeling. We defined the grids in a new model, and we defined materials, we defined cross-section properties, and we defined slab sections. In this lecture, we will do modeling, and besides modeling, we will assign some boundary conditions and diaphragms. We will look at the difference between restraint and constraint. We will check for possible modeling error after completion of modeling, that is after completion of adding frame and cell objects. We will then model staircase, and then we will look at some theoretical concept for next lecture on earthquake demand for buildings. So before starting the topics for today, let us just look what are stiffness modifiers. These stiffness modifiers, I prepared this slide to present in the previous lecture, but because of time constraint, I could not present about stiffness modifiers. So let's just look at stiffness modifiers in this lecture, and then we will go to our actual topics for this lecture. So what are stiffness modifiers? Stiffness modifiers were first introduced in IS 1893 Part 1. In the updated version of IS 1893 Part 1 code, which was done in 2016, the stiffness modifiers was introduced. Before that, the previous versions of 1893 did not state anything about stiffness modifiers. Stiffness modifiers are used to account for the reduced moment of inertia of the cracked section. That means when a building is subjected to earthquake shaking, the building is designed in such a way that we allow for the deformation of the building beyond the elastic range. That means we allow for the deformation of the building, we allow for damage in the building, and that causes the cross-section elements of the building to crack. And as the concrete elements of the building crack, the gross moment of inertia of those sections are reduced, and this causes a reduction in the moment carrying capacity of those cross sections. So to account for this reduced moment carrying capacity, to account for the reduced cross-sectional stiffness of those members, the concept of stiffness modifiers were introduced. These modifiers should only be considered for the structural analysis and not for the design portion. The modifiers are only for ultimate condition, that is for seismic load case. We do not use the stiffness modifiers while doing serviceability checks. And two impacts of stiffness modifiers on overall analysis. So what effects do we see in the building when we introduce stiffness modifiers? The first is that when we introduce the stiffness modifiers, the gross stiffness of that element is reduced. And due to the reduction in the stiffness, the structure becomes relatively flexible. And that means the structure will attract lower seismic forces. As we can see here, since we are considering the reduced moment of inertia, the overall stiffness of the structure will reduce, because the stiffness of each element for which stiffness modifiers have been defined will reduce in stiffness, and when we sum the reduced stiffness for the whole building, then the overall stiffness of the building will also be reduced. Due to the reduced stiffness, the structure will be relatively flexible and hence will attract the lower seismic forces. That is because we know that the time period of the building has the formula 2 pi root under m by k. So if the mass is constant, the time period is inversely proportional to the stiffness of a building. So when stiffness reduces, the time period increases. And when the time period increases, it attracts lower forces, because time period of the building and the amount of seismic forces also has an inverse relationship. And another effect of introducing stiffness modifiers is that drift of the structure will increase because it is relatively flexible. While the structure attracts lower seismic forces, the effect also can be seen in the increased drift of the building. These two are the major impacts of stiffness modifiers on overall analysis. In IS 1893 Part 1 Clause 6.4.3.1, The clause states that for structural analysis, the moment of inertia shall be taken as in reinforced concrete and masonry structures, 70% of gross moment of inertia of columns. That means stiffness modifier will be 0.70 for columns and 0.35 for beams. That is in 35% of I gross of beams. And while in contrast, when we design steel structures, we have to take the gross moment of inertia for both beams and columns. So this is about stiffness modifiers. So restraint versus constraint. Before going into this part, let us go to our ETABS model and then do some modeling. I will escape from this presentation and I will start ETABS. As we saw in the opening slide, first we will do about modeling, and in modeling we will add some frame and cell objects, and we will also model a staircase. I could have written this number 4 action in number 2. We will model a staircase, and then we will check for some possible modeling error. So in recent models here, I have a residential training building. Since this was one of the projects which I worked on recently, it is given here. I can just click this here and this file will open. In my computer, I can experience some lag while using ETABS 18 version. I haven't tried ETABS 19 version yet, but I can experience some lag while working in this version, but that should not be a problem when we are doing exercise. So we defined grids and we defined materials and cross sections in our last lecture. Now let us continue with modeling. In modeling, first let us go to the bottom and see some options here. In the cornermost we have units. If you click on these units and see metric SI defaults, we already chose units in the beginning. So if you click on show units form, it will give a list of units, what unit is used for what item. That is for section dimension, for displacement, for forces. You can see it from here. Let me just close this. And here we have an option: one story, all stories, or similar stories. If you click on one story, then whatever modeling or whatever assignments that you do on this model will only be applied to that particular story. In all other remaining stories, there won't be any effect. If you select all stories, whatever assignments or whatever modeling, whatever assignment of loads, whatever selection that you do on one story, the same thing will happen to all other stories. And similar stories means if you have assigned a master story while defining story grid data, and if you are working on that, then when you make some changes to any one story, then those changes will also be made to all other similar stories. For now, let us take all stories. So first, let us model columns. We can go to draw, and we have option here, draw beam column brace objects. And in this option we have draw beam column brace, quick draw beam column, quick draw column, quick draw secondary beams, or quick draw braces. We don't have any secondary beams until now because we don't know if we need secondary beams as we analyze and design the structure. But for now, we don't have secondary beams and we don't have braces. We only have beam column and we have slabs. So first, let's draw columns. I will choose this option, quick draw columns. So let's just see what will happen when we choose that option. So after we click on this draw beam column frame and draw quick draw columns, here you will see properties of object form, and in these properties you have to choose which is your column, and then you have to draw that column. For example, in this property tab, if you click here, this drop down list will come, and we know that we defined our column as column 400 by 400. So let's just click on this column 400 by 400. The moment release will be continuous. We don't have to define any angle or plan offset in x and y direction for the now. Our cardinal point will also be 5 middle center here, and then we will draw object using grids. So I just chose the property, and now we will draw. You can draw by either clicking on these grid intersections. If you look here, since we selected all stories, I'm drawing on this story 1 2.85 meter height, but as you can see from 3D view, in this A5 grid, column is being drawn on all the 3 stories. I will click here, I will again click here, or I can do like this. I will just choose this, make a selection around the intersection of these grids, and then column will be automatically added to all of these. Then I click escape. So let me go to my AutoCAD diagram for this. I showed you the plans of the building in our demo class, or I think in our demo class. We know that our structure is a 2.5 storied building. So if we go to our second floor plan, ground floor plan, first floor plan, and second floor plan, we see that we don't have column here, here, and here. We have a terrace here, we have some rooms and staircase here, but we don't have this column, and these 3 columns we don't have. So we have to delete those columns. So let's go to our model. Now we know that we have to delete. If you compare the grid, you will see that we have to delete these 3 columns. But be careful, when you are deleting the columns in that particular story, do not choose all stories, rather select one story only. And then you can go to our third floor, which is, or our second floor, which is story 3, 8.55 meter. Select these 3 columns and then click on delete. So our 3 columns are deleted, as you can see. So our modeling of the columns is complete. Now we will draw beams. To draw beams, we will again go to our first story. So our plan view is active. Click on this, move down in list arrow. This is story 2, 5.7 meter. And then again click on this. You move down to story 1, 2.85 meter. Okay, if you can see, I just forgot this. This is not our actual rectangular shaped building. We don't have column here also. So we have to remove this A1 grid column from all stories. So again, I go to our model. I check on this all stories. I select this particular column and then I click on delete. So all these columns are deleted. Now I will draw beam. To draw beam, if you look at this left hand side, there are shortcut keys. We don't have to go to this draw menu again and again. You can draw this with draw beam column brace option or quick draw beam column option. I will click on this quick draw beam column option, and same as previous, I will choose the property. Our type of line is frame. Our property is, we defined our beam as beam 230 by 350. Moment release will be continuous for the beams lying on the grid or the primary beams. We don't have any offset for now, and we will draw using grids. Again, this is all stories. Now we will draw beams on our grids. You can simultaneously see on the left hand side the 3D view. As you can see, while I am drawing only on the first floor, the beams are being drawn on the all floors because I have chosen the option all stories. So as I said previously, this program experiences lag in my laptop. When I'm using this computer, this is taking some time. So just have patience with me. I will just complete this drawing of these beams. So now you see this is taking so much time. It would be easy if I could draw like I drew those columns by making a selection around those grids. So let me see what happens. You can see as I drew like this, you can see the dotted lines which are the beams going to be drawn on the diagram. So I will just release my mouse and let me just check here these two lines. I have already drawn the beams if there are double beams drawn. If I select this and click delete, no, there is single, so I will just undo this. So now the modeling of the beams are completed. Again, you can see you have to delete these two beams because here is no column and this is not included inside the grids. So I will just make selection. When you make selection from right to left side, all the things that are just inside this circle or that you just touch are deleted. So this I will delete. And now let me go to third floor because third floor is only a half story. So I went to third floor. I will go again here and click on one story and I will delete these beams because there won't be these beams on the slab, top slab. So I made a selection and now I will delete these beams. So click on the 3D view and make it active and then click on this rotate 3D view option, and then by using the scroll option you can just move it around here, or by using the right hand click you can just rotate this view and see what will happen. This 3D view is drawn properly. So we have modeled our beams and columns. Now we will model our slabs. I will do this by using only one story option because this one takes much time. I will select this quick draw floor or wall option. Our property is slab 130. We don't need to define local axis for now. Then I will just click in between these to draw the slab. After that, I activated this plan view again and I will go to the next story below. I'll just click here. Although it lags, my work should be complete. Now I'm not going to draw a slab between these two grids 1, 2 and BC because we will have our staircase here. We will model our staircase here. I drew slab on top because this will be our staircase cover, but I want to draw slab here. So let me go to now go to first floor slab and do the same. And finally, after the modeling is complete, click on escape. Save the model. Now we have completed the modeling of beams, columns and slab. Before modeling staircase, let us just check if there are any modeling errors present until now. For that, you go to Analyze option and click on Check Model. You will see the software can perform joint checks, frame checks, cell checks, other checks, and fix option. So click on Select or Deselect All. All option will be selected. Also click on this Joint Story Assignment. Now everything will be checked and then click on OK. You can see here the software is creating analysis model. It will take some time for the model to be checked. And the check is complete now. Model has been checked. No warning messages were generated. That means our model is clean and it is error-free till now. So now let us go to modeling staircase. To model staircase, let me go to the base of the building, which is this zero elevation. We know our staircase will be drawn here. So to draw the staircase, we have to draw the landing slabs, and then the inclined slab portion. So how do we do that? Go to our AutoCAD and just zoom on this staircase portion. Measure the distance between the beginning of this first step and then this center line, DI, from here to here. This is 6 feet. 6 feet means 1.8 meter. And then again check the width of this landing slab also. You can press space for the same option from this center to here. This is almost 4 feet, that means 1.2 meter. So this will be 1.8 meter and this will be 1.2 meter. I will minimize this. So we can model this staircase now, or we can model this staircase. We will model this staircase in our next lecture because of time constraint. I also have to include some theoretical concept. So let's go to that. We will see what will happen if we model with or without staircase also. So for now, let's stop here. We'll save this model and I will minimize this. I will go back to my presentation. Because my last lecture was of about 1 hour, I am thinking to make relatively shorter, comparatively shorter lectures so that when people see those videos, they also won't get bored. We talked about stiffness modifiers in the beginning. Now let's talk about restraint versus constraint. We talked about the presence of noded elements, that is the presence of nodes and one-dimensional, two-dimensional or three-dimensional elements in finite element analysis. We also talked about degrees of freedom in the previous lecture. So we can say, or each degree of freedom in the structural model must be one of the following types: active, restrained, constraint, null, or unavailable. Among these, it's important to understand the difference between restraint and constraint because this will be the one that is most used while modeling. So what is the difference between restrained joints or restrained degree of freedom and constraint degree of freedom? If the displacement of a joint along any one of its available degrees of freedom is known, such as at a support point, that degree of freedom is restrained. So in a restrained joint, the restrained degree of freedom, we already know the displacement of that joint. In a restrained joint, we already know the displacement of that joint. For example, if we have a fixed support, we know that the fixed support is fixed in translation in all three directions and also rotations about all three directions. So we know the displacement of that joint and that displacement will be equal to 0. Such degrees of freedom are known to be restrained. The force along the restrained degree of freedom that is required to impose the specific restrained displacement is called the reaction. We know what it means by reaction. We have calculated reactions a lot in our undergraduate courses. And the force along that restrained degree of freedom are called reactions. Those reactions are determined by the analysis. So a restrained degree of freedom is one for which the displacement is known to us, and that displacement is 0 or any other value, and those are determined by the analysis. And in contrast, any joint that is part of a constraint may have one or more of its available degrees of freedom constraint. The program automatically creates a master joint to govern the behavior of each constraint. The displacement of a constraint degree of freedom is then computed as a linear combination of the displacement along the degrees of freedom at the corresponding master joint. For example, look at this example here. This is an example of a rigid floor slab. And in this rigid floor slab, suppose there are 4 joints, 1, 2, 3, 4. And let us suppose that the joints are connected to a master node in the center with rigid links. This is one rigid link, this is another rigid link, this is another rigid link, and this is another rigid link. In this case, let us suppose that the stiffness of these rigid links are infinitive. So what does this do to this rigid floor slab when all of its 4 joints are connected to a master joint by infinitely stiff rigid links? When we apply a displacement to this slab, suppose we give a displacement in this direction. So these 4 nodes will not displace independently, rather they displace simultaneously. And those displacements and the displacement of all these joints is affected by the displacement of this master joint. So as we can see here, any joint that is part of a constraint. Now these 4 joints are part of one constraint. We will know this constraint is diaphragm constraint. We will learn how to apply diaphragm constraint to our building also. In this diaphragm constraint, these 4 joints are part of that diaphragm constraint. Any joint that is part of a constraint may have one or more of its available degrees of freedom constraint. We have constraint the translation degree of freedom of all these 4 joints. We may also constrain other degrees of freedom also, but in this case, we have constrained the translation degrees of freedom. The program automatically creates a master joint. So when we constrain these 4 joints, this master joint is automatically created by the program itself. So this is the master joint, and these 4 joints are known as slave joints. The displacement of a constant degree of freedom is then computed as a linear combination of the displacement along the degrees of freedom of the corresponding master joint. That is, the displacement of this master joint now controls the displacement of these constraint joints. So this is the difference between a restraint and constraint. For example, you can see here, this is a 3D frame, and this is just an example. 4 different types of supports have been shown on the base of this 3D frame. Since this is a hinge support in it 1 degree of freedom, we know that hinge support restricts translation but allows rotation. So joint 1 restraints are U1, U2, U3, that is translation along x-axis, y-axis and z-axis respectively. Joint 2 is a roller support which only restrains the displacement of this joint in the vertical direction, that is U3 direction. It is allowed to rotate about all 3 axes, and it is allowed to translate along x and y axis. Similarly, in degree of freedom 3, in joint 3, we have a fixed support. Fixed support means all our 3 translations and 3 rotations are restrained. So U1, U2, U3, R1, R2, R3 all are restrained. And at 4 we have spring support. At spring support, none of the displacement are restrained, so the restraints are none. And the same is written here. Let us see how we can apply this restraint and constraint in our ETABS model, because we have to do it anyway. So it won't take much time. We will go to our ETABS model and apply restraint and constraint. To apply restraint, first go to your base plan, that is plan at z equals to 0 elevation. This is the base of our building. Select all the joints, and if you can see here at the bottom left corner, you see 14 joints selected. Go to assign, go to joint. Since we have selected joints, these will be joint assignments. So go to joint and restraints. You can see different types of restraints are available here that we just talked about in that previous example. We have a fixed restraint, we have a hinge, we have roller, and we have pin joints. Since our foundation will be of isolated footing type and that will be constructed in our real field also, we can assume the joints are restrained in all 3 translations and all 3 rotations. This we have to first be clear about what kind of joints or what kind of bases are we going to construct in the real field, and then you have to try to simulate that footing type or simulate that foundation type as much as possible. For that, when we design steel structures, we may choose pin jointed frames also or pin jointed bases also. In this case, we will choose our fixed support, and when we choose our fixed support, we can see that restraints are applied in all translations and all rotations. Click apply and click OK. Now if you hover on any of these nodes and right click and check on assignments, we see that restraints are applied in all three displacement. So we have applied our restraint. Now how do we apply our constraint, and where do you apply our constraint? Our constraints will be applied as diaphragms, because we are assuming that our slabs are rigid diaphragms. They will act as rigid diaphragms because we are not concerned with the outer plane deformation. We are not concerned with the outer plane displacement of those slabs. We are only concerned because our slabs will only act as those elements which will transfer our lateral forces to the moment resisting frames, and the slabs will act as a resistance to gravity loads. Beside those two options, the slabs do not perform any kind of function, so we are not interested in knowing its outer plane behavior. We are just interested in knowing its in-plane behavior. So for that, we have to assign constraint to all of our slabs at different levels. First, let us go to define and define diaphragms. Since there are 3 floors, we will assign 3 different diaphragms to each floor. We have already D1, modifier show diaphragm. Click on modify and show diaphragm. You see that it is a rigid diaphragm. Click on OK. You add another diaphragm, D2. This will also be rigid. Add another diaphragm, D3. This will also be rigid. Click on OK. So first, let us go to our first floor slab at elevation Z equals to 2.85 meter. In this plane, let us select all the joints. How do we do this? We go to select option, select. We will go to coordinate specification. And since this is our XY plane, we will click joint in XY plane. Nothing has happened. Let us just click on one joint, what you will see. So all the joints are selected on this. Okay, let's not assign our diaphragms right now because we are still left to model the landing slab for the staircase. This landing slab will also be on this same level. So after assigning or after modeling the staircase and those landing slabs, and then only we will assign the diaphragm constraint. So leave it as it is now. We have already defined the diagram. Let us just remember that in the next lecture, and in the next lecture we will just do the work of drawing those or assigning those diaphragms. Let me press escape. Let me save this model and then exit. So let us continue with our presentation. We have seen what is a restraint or constraint. So now let's come to earthquake demand and buildings. In our demo class, in our first of the all lectures, we saw what it meant by earthquake capacity of the building or earthquake demand on buildings. Earthquake demand is that force which is imposed in the building, and in our equivalent static force process or in our linear static procedure, that force is applied as a base shear at the base of the building. That is our earthquake demand, and capacity to the building is provided by designing the various elements of the building. So let's see here, in linear static analysis, the net effect of earthquake-induced inertia forces are represented in the form of design equivalent static lateral force. This force is also known as seismic design base shear. We already know this. And the value of this seismic design base shear is given by IS 1893 Part 1 2016 code in clause 27.2.1. Sorry, 7.2.1. According to this clause, buildings shall be designed for the lateral force VV given by this formula, the product of design horizontal seismic coefficient AH and seismic weight W. I will go through this part a little faster because if you are not able to catch up with all this formula or what are the values of different factors, then you can go to these particular clauses on the code and look through yourself. So base shear is given as the product of these two factors. Design horizontal seismic coefficient is calculated from the same code, clause 6.4.2, and seismic weight is calculated from the same code, clause 7.4. All the things that we will be learning now in the rest of this lecture are all based on IS 1893 Part 1 2016 code, and I won't be repeating that again. The design base shear remains the primary quantity involved in force-based earthquake-resistant design of buildings. We can design any structure either based on the forces that are applied on the structure or based on displacements that are produced in the structure. Since we calculate a design base shear in this linear static analysis, it is a force-based method of design. So how do we calculate seismic weight? You can go to clause 7.3.1, which says that for various loading classes specified in IS 875 Part 2, that is the code for imposed loads on the building. For various loading classes specified in IS 875, design seismic force shall be estimated using full dead load plus percentage of imposed load as given in table 10. Table 10 I have written here. So what weight of the building acts as a seismic weight, or what weight of the building is specified as seismic weight? Design seismic force shall be estimated using full dead load. So all the dead load takes part is seismic weight of the building, but in case of imposed loads or percentage of imposed or live loads, only a certain percentage of those loads shall be included while calculating the seismic weight. So if you see on table 10, if the value of our imposed uniformly distributed floor loads is less than or equal to 3, only 25% of those loads is taken. And if our imposed loads, the magnitude of our imposed load is above 3 kilonewton per meter square, we take 50% of those loads. So to determine seismic weight, full dead load or all of the dead load of the building is included and only a certain percentage of the live load. If you look at clause 7.4.1 seismic weight of floors, the code says seismic weight of each floor is its full dead load plus appropriate amount of imposed load is specified in 7.3 that we just saw now. While computing the seismic weight of each floor, the weight of columns and walls in any story shall be appropriately apportioned to the floors above and below the story. That is, half of the weight will act for one story and half of the weight will act for another story. Any weight supported in between stories shall be distributed to floors above and below in inverse proportion to its distance from the floor. And in clause 7.3.6, there is about interior partitions. You can go through this by yourself. So design base shear is horizontal coefficient into seismic weight. We know now how to calculate seismic weight. Now let us see how do we calculate the coefficient. So the formula for our horizontal seismic coefficient is given in clause 6.4.2. This AH is equal to Z by 2, SA by G, R by I. So what are these different factors? The Z is the seismic zone factor which is given in table 3. IS code has classified all the Indian area into 5 zones. 1, 2, 3, 4, 5. But zone 1 and zone 2 have been merged and now there are 4 zones, 2, 3, 4 and 5. 5 zone is the most critical zone in which the hazard level is the highest. So for highest hazard level, the earthquake induced forces also have to be the highest, and for that the factor is also the highest, that is 0.36. I is the importance factor of the building. Importance factor is given in IS 1893 part 1 to 5 for the corresponding structures. When the building is more important or the building is such that those will be used immediately after the earthquake, for example schools, hospital, those are the most necessary buildings and those buildings have to be used those buildings will be occupied immediately after any earthquake event. For such buildings, the importance factor is high. For example, 1.5 for critical and lifeline structures, 1.2 for business continuity structures, and 1 for the rest. As you can see from this formula, when the zone factor is increased, the coefficient increases and hence the design base here also increases. When the building is an important building, we will use a high value of importance factor. And when this importance factor increases, since this is on the denominator, again the coefficient will be increased and the earthquake induced lateral forces will also increase, and hence we have to design a more powerful structure or more stiff structure to resist those forces. This R is the response reduction factor. Response reduction factor accounts for overstrength and ductility in a building. We know that in the earthquake design of our buildings, we allow the building to damage, we allow for the dissipation of energy. So that is possible because of the property of ductility of those structures. So response reduction factor accounts for that ductility, and if a structure is highly ductile, that means it can withstand a large amount of earthquake induced forces without damaging. So for that we will have to design for a comparatively lower base shear. So for highly ductile buildings, the value of R is higher. Higher value of R means since R has inverse relation to this coefficient, the coefficient value will be smaller, and when the coefficient value is smaller, we get a comparatively smaller magnitude of design base shear. So we talked about Z, we talked about R and I. Now SA by G. What is SA by G? SA by G is the design acceleration coefficient for different soil types. This is another coefficient which depends upon the soil type. This is normalized with peak ground acceleration corresponding to natural period T of the structure. So this factor is dependent upon the time period of the structure and the soil type on which the building is being made or on which the structure will stand. In our IS code 1893, we have formulae given for calculating the SA by G, or we can also look at the graph and get those value of SA by G. You can see on the left hand side, we have SA by G value for 3 different types of soil: rocky or hard soil, medium stiff side soil, and for soft soil sites. And all these properties can be determined only after conducting soil test, and from this soil test report data we can know which type of soil is in our area, or which type of soil is being, on which type of soil is the structure being built. So once you determine the type of soil, there are 3 formulae depending on the time period of the structure. So for rocky or hard soil sites, there are 3 values of time period. There are 3 values of SA by G for different values of time period, and same is the case for other 2 types of soil. And soil type 1 means rock or hard soil, soil type 2 means medium or stiff soil, and soil type 3 means soft soil. This is in clause 6.4.2.1. You can look at it yourself also. So we knew how to calculate the seismic weight, we knew how to calculate this seismic coefficient. Now we can calculate base shear also, because base shear is equal to this horizontal seismic coefficient into seismic weight. So in the previous slide, we saw that the value of SA by G, or this design acceleration coefficient, is based on the time period of the structure. So how do we calculate the time period, the fundamental translational mode time period? So in clause 7.6.2, we are given formula for calculating time period for different types of building. In 7.6.2a, you have bare moment resisting frame building without any masonry infill. In B, you have buildings with RC structural walls, and in C, you have all other buildings. Since our structure is a reinforced concrete moment resisting frame building, we will use 7.6.2a formula, and in these 3 we will use our first formula for RC MRF building. The translational time period is given by 0.075 h to the power 0.75, where h is the height of the building. This excludes the basement stories, where basement story walls are connected with the ground floor deck or fitted between the building columns, but includes the basement stories when they are not so connected. So we will use this formula in this course to determine the approximate fundamental translational natural period. So here I have shown the response reduction factor for different buildings. I talked about how response reduction factor is larger for buildings with higher ductility and lesser for buildings with lower ductility. So ours will be a moment frame system, and in moment frame system we have four types: RC building with ordinary moment resisting frame OMRF, RC building with special moment resisting frame SMRF, steel building with OMRF, and steel building with SMRF. So our is a RC building, so we have to select between A or B. Is it an ordinary moment resisting frame or is it a special moment resisting frame? Since we will be detailing our building, we will detail the reinforcement in a ductile way, or we will perform the ductile detailing of the building. Our structure will be a special moment resisting frame, so we will take the response reduction factor to be 5. This value is higher as compared to ordinary moment resisting frame. And we saw how to find the value of SA by G by using formulae in the previous slides. Here you can see the diagram for determining the value of SA by G. On the horizontal axis, we have natural time period, which you will calculate using the formula that we saw in the previous slide. In the vertical axis, we have the value of SA by G, and this graph is for the three different types of soil. So you will just use your value of time period. You pick that. Suppose if we have got 1 second time period, we draw a vertical axis. We go to that graph, which is the soil of your site. Suppose if the soil in your site is medium soil, we will go to this second graph. And from this second graph, we will draw an horizontal line. And from this horizontal line, we will determine the value of SA by G. So let's see what were those factors. Again, the seismic design base shear depends on the seismic hazard at site of the building, represented by the seismic zone factor. Z is divided by 2. You saw there Z was divided by 2 because the formula was Z by 2, SA by Z divided by R by I. Z is divided by 2 to convert maximum considered earthquake to design basis earthquake. So higher the hazard level at our site, higher the value of zone factor. In keeping with the philosophy of increasing design forces to increase the elastic range of the building and thereby reduce the damage in it, courts tend to adopt the importance factor for effecting such decisions. So higher the importance of a building, higher will be the importance factor, and when we use a higher value of importance factor, we are increasing the design forces to increase the elastic range of the building. The net shaking of a building is a combined effect of the energy carried by the earthquake of different frequencies and the natural periods of the building. Courts reflect this by the introduction of structural flexibility factor, which we saw as SA by G. And finally, to make normal buildings economical, design codes allow some damage for reducing cost of construction. This philosophy is introduced with the help of a response reduction factor, which is larger for ductile buildings and smaller for brittle ones. So these are about our factors that are used to calculate the design seismic horizontal coefficient, which in turn is used to calculate the design seismic base shear, and that base shear is the earthquake demand on building. So this is the end of our presentation. In the next presentation, we will continue with the modeling of our structure. We will model staircase, we will model diaphragms, and then we will learn about load pattern, load cases, and load combination. We will see what are the differences between them, and we will learn how to calculate the loads and apply those loads to our structure. So this is the end of our presentation. Thank you.